Hello students, today I will start a next unit which is on fluorescence. Fluorescence in itself a very exciting subject, something which is related with colors, something which is related with analysis of some special samples, some special materials that can give this behavior, change in colors. We will study how fluorescence is possible, what is the basic principle, how fluorescence can be analyzed, and what are the applications. Kasha's rule we will study how time dependence or time independence measurement can be done in this unit. In this unit we have first Weisbrod introductions, Hertzberg-Taylor theory, then fluorescence spectroscopy, Kasha's rule, the meaning of quantum yield, non-radiative or radiative transitions, Jablonski diagram, and time resolved fluorescence and determination of excited state in lifetime. Comparatively smaller unit is there for this. The aim of this lecture is to introduce basics of fluorescence, the meaning of fluorescence, the difference between various terms we know since childhood, and basic what is fluorescence and what is the applications, why we want to study this. This is the basic of this first lecture. I think all of you have come across the fluorescence materials, the materials which can glow even in absence of light, even if used. Most of the time, whenever I'm talking about fluorescence, we must know we have many other properties also of light. For example, absorption, transmission, reflection. Fluorescence is different than others. If something is absorbed, can be checked by eyes, or if something is emitted, this will be checked. Similarly, transmission can also be checked. Here I am saying fluorescence. Fluorescence is giving you different emission which is based on absorption. From the last 20 years, a remarkable growth has been done in fluorescence studies, especially in biological sciences, and now a lot of work application have been developed, work have been done in electronics, also optoelectronics. Optoelectronics and medical sciences both are growing well, are doing well in the field of fluorescence. They are utilizing fluorescence for many purposes. Many of us now know we are using high definition cameras and use of light and everywhere. So it is growing field. We have done a lot in fluorescence spectroscopy, time resonant fluorescence, and this is considered to be primary research tool in biochemistry and especially in biophysics also. Fluorescence is now a dominant methodology and used extensively in biotechnology. Flow cytometry, medical diagnosis, DNA sequencing, forensics, genetic analysis, fluorescence detection is highly sensitive, and there is no longer the need of expense and difficulties of handling radioactive tracers. for most biological measurements. The purpose is this method is not that much harmful as radioactive rays, because initially for the same we want to carry out the same measurements as now we are doing with fluorescence can be done with tracers also, radioactive tracers, because they give radioactive rays and can be checked. But now we are doing the same work with fluorescence. In the fluorescence we handle only visible light or something. There has been a dramatic growth in the use of fluorescence for cellular and molecular imaging. Fluorescence imaging can reveal the localization and measurement of intercellular molecules, sometimes at the level of single molecule detection. You can measure even a single molecule. All of you are aware with this word luminescence. Some materials give luminescence property. It glows. Basically, the meaning of luminescence is the emission of light from any substance and occur from electronically excited states. Luminescence is occur due to electronically excited states. Basically, this divided into two categories: fluorescence and phosphorescence. Whether your output is fluorescence or phosphorescence, this depends on nature of excited state. In fluorescence, a molecule is irradiated with light whose energy correspond to the energy difference between its ground state and one of the excited state. So whenever you give energy, whenever you supply energy to the molecule may absorb energy if you are having the energy which is correspond to energy difference between ground state and excited state, one of the excited state. Here we have shown in the figure the energy is equivalent to this excited state. So whenever you give energy, your particle move to second state. Absorption of a photon can occur and rearrangement of molecular electron distribution occur as it reaches to excited state. Molecule electronic distribution occur. For example, an electron may be excited from a molecular orbit to molecular orbit, next one to orbit, because the light absorption only involves the movement of electron, no nuclear rearrangement, and electron are light, approximately 1 upon 2000 times mass of proton. Light absorption is very fast process. It is so much fast that 1 femtosecond is needed for this event. Once excitation of molecule has occurred by absorption of energy, the molecule can subsequently return to the ground state by losing its energy. Now there are two ways to transfer again here. It can go on the excited state on giving the energy, on supplying the energy, and electron can come back by one of the ways. In the first way, they can transfer heat to surrounding without any radiation. That is called radiationless transition. Most of the time, in most of the sample, this happens. Whenever we give the energy, it moves to excited state and finally move to ground state, and we never see any luminescence and something. But there are a class of materials, a variety of materials in which the emission is in the form of light. If we are having emission in the form of light, then it may be fluorescence or phosphorescence. I will discuss the basic difference later, but right now you understand two things. The emission either be without radiation or emission with radiation. If emitted without radiation, that is okay, but emitted with radiation, we are concerning with this. Either path may dominate depending on nature of molecule. The molecule quantum yield can range from 10 to the minus 5 to 1. Quantum yield we will discuss detail in the later on, but here quantum yield is what is emitted divided by what is absorbed. Nearly 1 means whatever is absorbed, most of them is emitted. That is called very good emission. 2 minus 10 to the minus 5. It can vary. Interesting event here is shown in the terms of atomic structure. Atom consists of nucleus and then electrons surrounded by. If you take this to learn the event, to analyze the event, in the step 1, there is actually 3 steps. In the first step, energy from the source strike on orbiting electrons. So we strike the electrons, electron strike on orbiting electrons, light strike on orbiting electrons. The electron excited to higher energy state and then fall back to ground state. Now the thing is, energy released either in the form of light or internal transitions in the form of heat. If emit in the form of light, that is called fluorescence. To learn more detail about fluorescence, we should also know some particular thing about electronic states. Electronic state generally reflected by S0, S1, S2, where S indicates singlet excited state, in which electrons remain paired during the excitation. Electron remain paired means spin is 0. Total spin is 0. If total spin is 0 means if two electrons are possible at one place and both are paired, then the energy, one is up, second is down. One spin of one electron is up, the second must be down. This is called singlet excited state. There is a possibility of another kind of excited state, that is called triplet excited state. The electron spins are parallel and the total spin will be 1. At each of these electronic energy levels, the fluorophores can exist in a number of vibration energy levels, and this is depicted by 0, 1, 2. They extend to S1 and beyond, and the number of stages are very crowded. It is important to note that the energy level can be modified by interaction of fluorophore with surrounding molecules. So we have learned here about singlet state and triplet state and how electron can move from singlet state to triplet state. As we have already discussed, excited singlet state, the electron in the excited orbit is paired with opposite spin. To the second electron in the ground state, return to ground state in spin allowed occurs rapidly by emission of photons. The emission rate of fluorescence this is called fluorescence. The electron move to the ground state when excited orbitals are paired, means singlet state. When this happens, rapidly a photon emitted. The emission rate of fluorescence are typically 10 to the power 8 second inverse, so that typically fluorescence lifetime is nearly 10 nanosecond. Fluorescence lifetime is very small. On the other hand, phosphorescence is emission of light from triplet excited state to ground state, in which electron in the excited orbit has the same spin orientation as the ground state electron. The transition to the ground state are forbidden and the emission rate are slow, 10 to the power 3 to 100 second inverse. Very slow rate is there. So that phosphorescence lifetime are typically millisecond to seconds, even longer than that. We have seen many toys that glow in the dark. We can purchase many stars or glowing objects that can be put in the room in the dark that have very long time. That is so those are not giving fluorescence. Actually, those are giving phosphorescence. Phosphorescence occurs from triplet state to ground state. In other case, single in the previous case, the fluorescence occurs from singlet state to singlet state. It should also be clear that phosphorescence is usually not seen in fluid solutions at room temperature because there exists many deactivation processes that compete with the emission, such as non-radiative decay and quenching process. We will discuss those processes in later on also why fluorescence doesn't occur. But normally in many solutions, fluid solutions, difficult to see phosphorescence. We should be distinguished between phosphorescence and fluorescence, but should be also be noted that it is very difficult to differentiate between the two. Transition metals ligand complexes which contain metal and one or more organic ligand display mixed singlet triplet states and display intermediate lifetime of 100 of nanosecond for several milliseconds. So it's a long way to go. Sometimes phosphorescence and fluorescence even close to each other and difficult to understand. It is also an interesting fact that fluorescence typically occur from aromatic molecules. Some typical fluorescent substance shown here The widely encountered fluorophore in quinine. Suppose quinine, which is present in tonic water, if one observe a glass of tonic water that is exposed to sunlight, a faint blue glow is visible. This is due to fluorescence. This glow is more apparent when the glass is observed at night. So there are many devices, many drugs that can give you fluorescent behavior, but is giving at sunlight when exposed to sunlight. Whenever we strike light on any sample, then following light absorption, several processes usually occur. We will discuss this process here. The term fluorescence refers to one type of luminescence, and luminescence broadly defined is light emission from a molecule. But we have several types of molecules of luminescence. For photoluminescence, chemiluminescence, electroluminescence, thermoluminescence is not mentioned here but can be added. For example, photoluminescence, it is clear from the name, when light energy or photon simulate the emission of photon. It's called photoluminescence. We strike the light and we observe the luminescence. As I discussed here, in a tonic, if quinine is there, strike the sunlight, and you will see the behavior. Chemiluminescence is also there. It is defined as when chemical energy simulate the emission of photon. This also include bioluminescence, as seen in fireflies, many of the sea life. Electroluminescence, when electrical energy or strong electric field simulate the emission, that is called electroluminescence. Thermoluminescence, if we heat the some substance and we get the luminescence. Now we have many toys or coffee cup. When you pour the coffee in the cup, it will glow. Thermoluminescence. Fluorescence is there. It is a typical example of photoluminescence when light raises an electron to an excited state. The excited state undergoes rapid thermal energy loss to environment through vibrations, and then a photon is emitted. The process of photon emission compete for non-radiative process including energy transfer and heat loss. When the term fluorescence is used, the same method for measurement can typically be applied to any of other categories. In this lecture, we have studied luminescence term, then we have studied phosphorescence and fluorescence difference. We have studied singlet and triplet behavior, and in the last slide we have discussed many type of luminescence behavior. We have discussed possible applications, potential of fluorescence for sample analysis and medical purpose or electronics devices, and find differences between these events that may appear with the molecules. In the next lecture, we will study diagrams, how the diagrams can take place. We have already discussed here two types of radiation, which is radiation, which is it can be transferred only heat, no light, or with luminescence, without luminescence and with luminescence, and in luminescence, fluorescence and phosphorescence. Thank you.